Okay, so what I'm demonstrating here is the difference between static friction and sliding or rolling friction. So we've got our spring scale here, we've got a 500 gram mass on our sliding block, and I'll make sure that I'm on the Newton setting here. So watch that plunger there, see what happens as I get it going. So I'll go ahead and start. And what you should have seen is that to get started, the plunger went pretty far, went all the way almost to about 2.5, and then once I keep it going, it should take about 1.5 newtons. So sliding friction was to get down to that 2.5 newtons. It took more force to get it started, and then once it was sliding along, then it maybe only took about 1.5 newtons to keep that going. Same logic applies to the skateboard, that to get it started rolling, that's our static friction force that's being overcome. It takes more force. There should be a spike on the Logger Pro, and then it should require less force to keep it rolling along. Okay, I am going to demonstrate how to do our Skateboard Lab. It's pretty straightforward. It's actually very similar to the sliding block lab. I wanted to point out a couple things that you need to be aware of though. First is the sensor setting. Take a look at that up there. We've got plus or minus 10 newtons and plus or minus 50. Since we're dealing with a larger mass compared to our previous lab, the inclined plane lab, you're going to actually want to make sure it's set to 50 on there. Basically that just means you're using the right measuring stick, so to speak. So the most important thing about this is don't break the sensor, please. The way you do that is by holding onto the sensor box, not onto the cord. You can see actually this one's an older one from last year. It's a little bit frayed there on the outside. Not sure if this one still works. I'll have to test this out, but mostly you can break the wires inside of there if you hold it here and pull somebody at all on the skateboard holding that outside wire. So you're holding the sensor box. You get your rope. Just put it, you should get a little loop of rope like this, and then put it around the axle. That'll give you a nice point to pull from. Let's see if I can get that. And then put that into your hook. Now, obviously this represents the mass of one of you who is going to be sitting on here. I'm going to show you the computer view of what this should look like and what you're analyzing in a second. But the next pointer I wanted to give you about how to pull this is make sure you're not pulling like that or like that. You want to make sure that the only component to your force applied or your force of acceleration is directly in front of it, not up, not down, because then you're messing with the normal force and with the force of gravity, or you're kind of adding or subtracting from those a bit. So you're trying to pull that as level as possible. And just like in our inclined plane lab, once you get this started, you want to just keep it at a consistent of a pace as possible. You can try many trials to get this right, to make sure that you get a graph that looks good. You ultimately want to take three trials and get the average of each of those. So let me go to the computer and I will show you how to analyze it. Okay, so I'm out here in the hallway. I'm going to pull our skateboard along here. I'm going to press play in just a moment and show you what it looks like to start it and keep pulling it. Okay, so first thing is to auto scale. You might need to do that on your first try. I already auto scaled this down here. So auto scale, we can see that peak right there. We're going to examine that. Let's move that out of the way. Getting 11.59. That right there is the force of static friction. It's how much force you had to apply to the skateboard to get it moving, to go from being static to dynamic. And you notice that it went way down once we got that moving, and it stayed at this relatively consistent level. Here's where it'd be lovely if you could put a best fit line on this whole thing. What I'm going to do is I'm going to pick a number that's kind of right in the middle of all this. We'll go right maybe here. That's a force of 6.19 newtons if you look over there on the left. So this would be my force of rolling friction. That is my force of static friction right up there. So I'm going to try it again, see if I get something relatively similar to about 11.5 and 6.2, I think is what I said, for this one right here? Okay, I'll give it another try. Okay, and obviously when it goes down there, that's when I stop pulling it. You guys might be able to pull a little bit better than the one-man show I've got going on here. So auto scale, it's actually pretty good already. And if we take a look, this is our static friction peak right here, 11.41. That's extremely consistent. And right in the middle, let's say kind of right in the middle, right around here, probably looks good again. So 6.13. 6.5, one of those numbers might be a good one to write down. This is obviously the less scientific, less precise way of calculating this, but to figure out exactly what the average of this rolling friction is here. So you want a relatively level looking graph right here before you pick one of those values, and you can write that down in your notes. Okay, so what I'm showing you here is kind of a preview of what you should see in the Skateboard Lab. So pretend that this fridge here is our skateboard, and you are actually pulling on the skateboard, not pushing on it like this guy is pushing on this fridge. You should see that, I'm going to actually use the small crate instead. You should see the normal force directed in opposition to the applied force down here, and you should note that right now it's at rest. It's not moving because those forces are in balance. Well, as soon as I start applying a force or accelerating, remember FA is the force of acceleration, the force applied. You can use those kind of interchangeably. And then the force of friction is our FF. And as I increase my force applied, the force of friction increases to counter that or to oppose that. But eventually we should reach a limit of the force of friction. Watch that red arrow. Okay, so I'm going to stop that for a second. You should have seen that that red arrow is getting larger and larger until all of a sudden my force applied overcame it. The box starts to move and the force of friction decreases. That first initial pushing I'm giving, I'm trying to overcome the force of static friction. That's the force that's resisting it from moving. And then as soon as it's moving, notice that there's less friction slowing it down. And sorry to wreck your eardrums there. There's a smaller frictional force. That's the sliding friction. In the Skateboard Lab, you've got wheels on this thing, so it'll be rolling friction. But you should see that that number goes down for how much force you have to apply to keep the skateboard moving after you start it moving.